welcome to this episode of Night Sky News with me, astrophysicist Dr. Becky Smethurst. This is the show where we chat about everything you should look out for in the night sky in the coming month, and we recap what's been happening in space news in the past month. There are chapter titles down here if you want to skip ahead to any specific news story, and also any scientific articles or papers that I mentioned will be linked in the video description down below. So without any further ado, let's kick things off and start by looking up. First, just a quick reminder from last month's episode that Jupiter is going to be in what's called opposition this Friday, the 20th of August. And essentially what that means is that it's going to be very bright on the sky. And that's essentially because it's perfectly lit right now from our perspective. It is in the exact opposite part of the sky from the sun, 180 degrees round from it. And essentially Earth is passing between Earth and Jupiter so that it is perfectly lit from our perspective. Someone in the comments of last month's video actually asked whether that would mean that the Earth was capable of casting a shadow on Jupiter, sort of like, like eclipsing the sun from Jupiter's perspective. Earth is unfortunately too small and too far away from Jupiter to do that, to actually have any defined shadow at that point. And also the alignments are not quite right for the planes that Earth and Jupiter orbit in. If you want to spot Jupiter, it's actually visible throughout the night right now, but you'll want to look, in the southeast as it's rising if you're looking for it before midnight, or you want to look for it in the southwest if you're looking for it after midnight. It'll be the brightest thing in the sky after the moon. And you'll notice that handily the moon is once again very close by over the weekend, making finding Jupiter and Saturn as well just that little bit easier. So on the 20th, on Friday, the moon will be closest to Saturn, but then by Saturday the 21st and Sunday the 22nd of August, it's going to be closest to Jupiter. Now, the problem with the moon being so close is that it's very bright, so it actually washes out Jupiter and Saturn a little bit, so they don't appear as bright as they could. That's because the moon's going to be almost full on Friday and actually be a full moon by Sunday, the 22nd of August. It's actually going to be a blue moon as well, which doesn't mean that the moon will look blue. It's because it's the fourth full moon in a season. So in this summer, it's the fourth full moon. So if seasons are around about 3 months long, you'd expect 3 full moons normally. But a full moon happens every 28 days, right? So if you wait about 3 to 4 years or so, that cycle eventually catches up with itself and we end up with 4 full moons in a season every occasionally. So hence, once in a blue moon. And so what it means is that yes, it is going to wash out Jupiter and Saturn a little bit this weekend, but I would still recommend that if you don't really know what you're looking for, use the moon this weekend. Find Jupiter and Saturn, make sure you're like, okay, that's what they are, that's where they are from my house window. And then by next weekend or throughout this week, as the moon moves away from that part of the sky, you'll then know what you're looking for and you'll be able to appreciate them properly in all their glory, shining as bright as they possibly can be. And it's great that the moon is moving out of that part of the sky because on the Sunday, the 29th of August, Jupiter is going to be putting on a show, or at least Jupiter's moons are going to be putting on a show. For all of you in Europe or Africa, or even maybe that most eastern tip of South America as well, you should be able to spot this. And it's specifically those of you with telescopes as well. So those of you maybe you're looking for an excuse to break out a telescope you've bought recently or had hanging around the house for too long, this would be the perfect time because Jupiter's moons, Europa and Ganymede, their shadows are actually going to be crossing Jupiter's face on Sunday the 29th of August, along with the great red spot on Jupiter as well. So you should have the most amazing view of Jupiter that night. Now, Europa's shadow will disappear around about midnight UK time. It'll actually be the same time as the great red spot. It's just coming round the other side. By 1 a.m. though, the great red spot will be fully visible and also Ganymede's shadow will be nicely in the middle too. So make a night of it on the Sunday night if it's clear. From around about 11:30 at night to about 1:30, sort of that Monday morning, you'll have an absolutely fantastic view. And if you do manage to spot it through your telescope, send some pictures my way as well, like so many of you did, of the Toenail moon and Venus in August, just looking absolutely gorgeous together at dusk. I mean, you lot captured some really spectacular shots. But if you missed it, not to worry, because you're going to have another chance on Thursday the 9th of September and Friday the 10th of September to see Venus pairing up with this tiny sliver of a crescent moon that reminds me of a toenail. It's so poetic, isn't it? I know so many of you hate it, but I think it's the best description of it. The closer you are to the equator, the higher this is going to be in the sky. Up here in the UK, for example, it's going to be very low on the horizon and disappear very quickly after sunset. One of the best ways to know like how long Venus is going to be up for you, and also if you're looking at the right thing when you actually try and spot it as well, is by downloading a night sky app. And so this video is sponsored by The Sky by Redshift. It detects your location and which direction you're facing and essentially shows you the position of all the stars, constellations and planets directly in real time. So if you're thinking, oh, that bright star over there, is that actually Jupiter? You know, you can hold your phone up to the sky and actually check that that's what you're looking at, or you can go, oh wait, no, Jupiter's over there. The app also lets you see what the sky looked like in the past, like on your birthday or something, or on a date in the future at any location in the world. You know, in case you want to check what you'll be able to see next weekend, or maybe for your next holiday or vacation when you know you'll be away from light pollution. It's great for beginners and pros alike, plus the best bit is that it's completely free to download from either the Google Play Store or the Apple App Store as well, the links for which are in the video description down below. But that's enough with looking up at the night sky. Let's come back down to Earth with a bump and chat about what's been happening in space news in the past month. All right, those of you that keep an eye on the newest and latest astronomy papers that get published might have spotted a paper from yours truly this month. My research on the outflows from the regions around growing supermassive black holes in galaxies that have never merged with another galaxy was accepted for publication this month, and so I've posted it on the Astronomy preprint archive, so it's free for everyone to read. If you want to read it, that's amazing. I'll put a link in the video description down below, but please remember, these papers are not written for the general public. They are written for other experts, other astrophysicists. So if instead you want to hear me explain what I found in a much easier way to understand, then you should check out my video from a few weeks ago where I actually presented this work at an astronomy conference and explained to you guys what I'd actually found in my latest research. So I'll link that video up here in a card, but also in the video description down below along with the paper. But I'm really proud of this paper. I really like it. I hope it gets a lot of attention from the wider, astronomical community, and I maybe hope it starts racking up some citations too. But enough about my research. Let's talk about exomoons, which, can we just look at that word for a minute? How cool of a word is that? So let's start with an exoplanet. That's a planet in orbit around another star in our Milky Way that's not the sun, right? So it's not a planet in our solar system. It's in its own star system, right, around another star. And we've found thousands of these things over the past few decades, and the hope was that eventually we might be able to detect an exomoon. A moon in orbit around an exoplanet in orbit around another star in our galaxy. Now, there's been a couple of claims over the years that maybe this had been found already, most notably from Tichy and Kipping in 2018, and they used the Hubble Space Telescope to observe a star called Kepler 1625 when they knew that a planet, Kepler 1625b, was going to pass in front of it. And that's because that planet had already been discovered by the Kepler Space Telescope, hence the name of the planet. So they knew exactly when it was going to pass in front. And they could record the brightness of the star and see the brightness of that star dipping because the planet was passing in front of it. And they claim that the shape of that dip that they recorded couldn't be explained by just a planet. There had to be something extra there, and proposed the idea of an exomoon around Kepler 1625b. But then in 2019, Kreidberg, Luger and Bedell reanalyzed the exact same data and found that the planet-only model fit the data just as well as a model with an exomoon. There was no need for a more complicated model. It was a classic case of Occam's razor. So with the enthusiasm over that exomoon just reined in a little bit because of the doubt that's been cast over it, the news that this month that there's been an actual image of an exomoon published, well, that got me very excited. This was work by Benistian collaborators who used the ALMA array, a telescope made up of lots of individual antennae that detect light somewhere between the infrared and microwaves that we call sub-millimeter wavelengths. And we can combine the light from all of those individual antennae to make one huge telescope. And this is good because the bigger the telescope, the smaller the thing that you can see. And here is what Benistian collaborators saw when they looked at the star PDS 70. Now you're probably thinking, Becky, that looks nothing like a star, but bear with me. So the star itself is actually in the center of the image here. Stars themselves aren't that bright in sub-millimeter wavelengths that this image is taken in, but dust and debris are. And that's because the light from stars and protostars, like brand new stars that are just forming, they're giving out all this light in optical and UV. And then the dust and debris absorbs all that and then re-radiates it in the infrared and submillimeters. So that's much brighter even than the star at these wavelengths. And you can see that in this image, right? There's this bright ring around the outside, which is this dusty ring of debris, which we call a protoplanetary disk, essentially a bunch of rubble that could one day form a planet around this star. Now we've seen these before, loads. Here's a bunch of examples in various different stages of planet formation around different stars. And you can see in PDS 70 that there's actually a cavity in this protoplanetary disk where a planet or planets have already formed. In fact, if you zoom in a little bit, you can actually see one of those planets as that bright dot right there in the middle of that cavity. But what Benistian collaborators are also claiming to have spotted is that there's another little dusty debris disk around that planet. It's not just a pinprick of light, it's fuzzy. And so what they've claimed that little fuzzy disk could be is a proto-moon disk, a moon in formation around this planet, an exomoon. And they've not just done that, by squinting at this image funny, but actually by modeling the light in the image, subtracting it off and seeing what's left and confirming there is an excess of light around the position that you find this planet. So it's perhaps not, the first smoking gun of an image of an exomoon like you probably expected if you're familiar with perhaps the first ever image of an exoplanet that was taken back in the mid-2000s with the Hubble Space Telescope. But that was something around Jupiter's mass, right? It was big. Exomoons, though, are going to be so much smaller and less massive that, we're talking Earth mass, maybe even Mars mass or lower here for an exomoon. So I think it's incredible that we've even been able to spot something that might just be the fuzzy disk of an exomoon forming. And it's images like this that remind me why I love astronomy so much. Speaking of imaging things at mind-blowing detail, just 2 days ago on Tuesday, the LOFAR team, which is another of these huge big arrays, this time in the Netherlands and across Europe, did a big press release of over 11 papers, of a big data dump, essentially, that was looking at the burps from supermassive black holes in 20 times more detail than they'd ever been seen before. So I'm going to take the week to, first of all, read all of those papers, but then also chat to some of my colleagues that are on the LOFAR team that have been involved in all of this work, getting all the data ready for release and some of the science that's been done as well. So that'll be coming in my next video next Thursday, so keep an eye out for that. But for now, let's come a little bit closer to home for a bit and chat about what's been going on Mars, because this month, Perseverance drilled its first hole in the surface of Mars.
We got a hole to dig up here.
Better rein in those celebrations though, because the reason that it drilled a hole in the surface was to collect a sample of rock that could maybe one day be returned to Earth for us to study it. But when they looked at the little sample tube that was supposed to contain the rock, it was empty. Which obviously was a huge disappointment. It's supposed to core out a sample and store it in one of these 43 inert titanium tubes, but clearly, as we can all see, that didn't happen. So this whole process is autonomous because of the light travel time between Earth and Mars, right? Essentially, the mission control at NASA sends one single ping to the rover, which is essentially go through all the steps to collect rock sample. And it looks as if, the drill and the bit engaged okay. It managed to drill 7 centimeters down into the surface. It managed to get out the extraction tube okay, but then when it looked at the extraction tube, it was empty. And that had never happened, in lab testing here on Earth. So there's been a big investigation into what went wrong. And obviously the first thing the team did was actually check if the sample had just been dropped somewhere. All the places that the rover arm had moved, because this drill was sort of on the end of the rover's little robotic arm. All the places that it moved, just check the ground and just check to see if there's not just like this big cylinder of rock or pieces of it just littering the ground. There wasn't. Thankfully, it hadn't just been dropped. Then they used the camera on the end of Perseverance's robotic arm to just get a good look at that drill hole. And here is that image. The hole looks clean at least, but you can just see the material almost looks like sand, right? So rather than getting like a solid core of rock like the team expected, it seems as if Perseverance picked a rock where it was collecting sort of like almost like a fine powder or just very small fragments, which it didn't have a hope of holding on to. You can even see that, right? In the image, there's just this little pile of material at the bottom of the hole that was most likely the intended core sample, right? But it's just pooled at the bottom there. So after the investigation, the Perseverance team essentially concluded that they just got a little bit unlucky with the rock that they chose to drill into for the first time. So they're going to move on to their next sample location, which Ingenuity, the little helicopter that could, right, has already scouted out the location for them of this next sampling location and said, yeah, the rocks look promising there. They look sedimentary, like what we've practiced with on Earth as well. So fingers crossed that it wasn't a hardware problem, but it was just the rock that wasn't cooperating.
Couldn't have picked a worse spot to drill.
Sticking on Mars for a bit, but this time for a success story, because the InSight lander has managed to figure out the internal structure of Mars using Marsquakes. So cast your mind back now to high school science or geography, whichever class you learned it in, to how we figured out the internal structure of the Earth, right? That we've got the crust and the mantle and that liquid core and the solid core. And it's all to do with earthquakes. And there's lots of different types of earthquakes that can shake the ground, but they include P waves and S waves. And these are really fun to recreate on a slinky. P waves are what's called a compressional wave, right? I always remember because it's like a push wave and that's what you're doing to the slinky. And then S waves are your classic like wiggle wave, right? That causes shear through an object. And it's these differences between P waves and S waves that help us figure out the internal structure of the Earth, because S waves can't travel through liquids. So if you have an earthquake on one side of the globe, the exact other side of the globe, like the antipode, right, they won't be able to detect that earthquake there in S waves because those S waves can't get through that liquid core. You literally get this shadow region where you won't detect any of those. P waves, however, can travel through liquids and solids, but when they hit a boundary, they refract. They get their path changed just that little bit, and so you also end up with a P wave shadow where you don't get any P waves from an earthquake on the other side of the globe. And together those things helped us work out the structure of the Earth, right? That the core was liquid and how big the core was and how big the mantle was, etc. And this is exactly what the InSight team has done on Mars, except they didn't use earthquakes, they used Marsquakes, but it's the exact same principles. So InSight landed on Mars in 2018, and since then it's had this little seismometer on the ground which has detected 733 Marsquakes, all around about 3 to 4 magnitude on the Richter scale. Now that's lower than we'd expect on Earth in the same time frame, but that's because on Earth our earthquakes are caused by tectonic plates moving and slipping next to each other. On Mars, it doesn't have tectonic plates. Its crust is just one solid lump, right, that's been cooling ever since it formed 4.5 billion years ago. And as it cools, the rock shrinks. And so if there's fractures or fissions or just failures in the rock somewhere as it shrinks, the pressure on that is released and you get a little Marsquake. Now, the difference between the way that we figured out the structure on Earth and the way that we can figure out the structure on Mars is that on Earth, you can have seismometer stations, these stations that detect earthquakes, all around the globe, right? And so you can work out where the shadows are when an earthquake goes off on one side of the globe as compared to the other. On Mars, you've only got the one seismometer that came with InSight. So you have to get a little bit clever here. So InSight actually detects Marsquakes on the surface as it passes through the actual surface of Mars. But then it also detects them again after they traveled through the interior of Mars, bounced off a boundary like between the crust and the mantle or the mantle and the core, and back up again for InSight to detect them. So there's been 3 different papers published this month, all with this Marsquake data. One led by Nat Meyer-Endren and collaborators on the thickness of Mars's crust, one by Kahn and collaborators on the structure of the mantle below the crust, and one by Staehler and collaborators on the size of the Martian liquid core. Now, there's still a bit of uncertainty around these measurements because they're using this reflection technique rather than having multiple seismometers detecting all of these waves. So what it means is that the crust, well, it could have two boundaries in the crust. It could have two layers, and if it did, then it'd be about 20 kilometers thick. But if it has 3 layers, then it's 39 kilometers thick. Then you've got the mantle below that, and then a liquid core with a radius of 1,830 kilometers. It's nicely summed up in this little diagram. The yellow stars here are the locations of the Marsquakes that they detected, and you can see how those waves, shown by the thick red lines, bounced off the core and back up for InSight to detect. One of the things the team noticed, though, was a lot of these Marsquakes came from the Cerberus Fossae region of Mars, which is really interesting because this region was already one that was thought to have been volcanically active in the past. You know, we've seen sort of like little boulders like rolling down the hills around there that could have been dislodged by Marsquakes that could have come from volcanic activity. So it's interesting that that's where they're finding it. Perhaps there is sort of maybe a little bit of a rumbling of something still going on under the surface there. What the team really want to detect, though, is what they've dubbed the big one, right? Is a Marsquake, you know, that's well above 4 magnitude on the Richter scale. That would actually make their measurements much more precise because the quake would be that much more louder, for want of a better word, right? And that much easier to detect. So the uncertainties on their measurements would go down. InSight, still on the surface of Mars, still got its seismometer detecting these Marsquakes. It detects them every single day, right? So it's literally just a matter of time. All right, the big news this month. This study that's come out claiming to have seen behind a black hole for the first time. So this is a study that's been led by Wilkins and collaborators, and they've observed the X-rays from the region around a supermassive black hole in the galaxy 1 Zwicky 1, which is a dwarf galaxy a lot smaller than the Milky Way. It's only about 3,000 light years across as opposed to the 100,000 light years of the Milky Way. But its black hole is about 7 times heavier. It's 30 million times the mass of the sun. Now, supermassive black holes have what's called an accretion disk, which is essentially a load of matter that's orbiting the black hole that will eventually, you know, become a part of the black hole in the future. And this accretion disk is way out past, you know, what we call the event horizon of the black hole, that point of no return where we can no longer see anything. Now, this material in the accretion disk, because of the huge gravity around this black hole, it's accelerated to incredible speeds as it orbits the black hole. Because it's accelerated to incredible speeds, it has a huge amount of energy, and that material starts to glow in anything from optical to UV to X-ray light. It can also flare in X-rays too, if a particularly large clump of matter makes it, you know, into this accretion disk and increases the pressure, so the region around the black hole essentially burps to relieve some of that pressure, and you get this big flare of X-rays above the accretion disk. That's what they've claimed to have detected here, an X-ray flare, but also the light from the flare reflected off the accretion disk itself. But that reflection actually changes how much energy those X-ray photons have. It changes their wavelength because of a Doppler shift, essentially, because it's reflecting off material that's moving incredibly, incredibly fast. But also, you get a gravitational shift as well, just because of the intense gravity around the black hole pulling back on the energy of those X-ray photons. And so it gets stretched out, essentially, the wavelength of those photons because of the gravity of the black hole. And so you can actually tell where those photons have been reflected back from, those particles of X-ray light, where they've been reflected from on the accretion disk, depending on how much of a shift in energy they've had, either because of the fact that the material is moving or because of a gravitational redshift if it's come very close to the event horizon of the black hole. And that's what they're claiming to have detected here in this paper, right? All of these X-ray photons that have been shifted to different energies by varying different amounts of Doppler shifts or gravitational redshifts. And this is how they could tell that they detected a photon of light, a particle of light from behind the black hole, because it had been gravitationally redshifted the most as it traveled on a curved path around the black hole. This straight line that the photon should have taken was bent by the black hole's gravity so much that it came round from the backside so that we could detect it. Now, I know a lot of people got a little bit confused by that and got very confused when they just saw the headline of seeing behind a black hole, because it doesn't really make sense, especially when people picture black holes as actually holes. They're not holes, right? They were once three-dimensional, and we pictured the event horizon around them, that point of no return, as being three-dimensional as well. So if you want to picture this, it will be like me saying, okay, trying to see the far side of the moon. Say I got in a little spacecraft and went all the way around the backside of the moon and hid behind there. And then I had a torch that was sort of like flashing light every now and then. It would be like you still being able to see the light from my torch because it had been bent by the gravity of the moon to you on Earth. Now, of course, the moon does not have enough mass to actually do that, to cause that amount of bending of space-time to curve the path of the light that much. It's only really black holes that have a strong enough gravity, a strong enough curvature of space-time, a sort of gradient of gravity very close to them to be able to bend the light that much. And so that's how they've been able to see behind the black hole, because of this bending of light. It's actually what was modeled for the black hole in the film Interstellar as well, right? This loop of light at the top here is the light of this accretion disk around it, but bent by the gravity of the black hole from the back of it so that we can see it sort of at the top. This is a prediction of Einstein's theory of general relativity, right? And so this study from Wilkins and collaborators actually confirmed that. It's almost put a tick next to the interstellar rendering of that black hole. So if you've learned anything from me from this episode of Night Sky News, it's that behind a black hole would be a terrible hiding place for a game of hide and seek, right? So I'm going to leave you with that little nugget of information, because that's all I have for you for this week. Remember, if you snap a picture of the night sky, to send it to me over on social media, either on Twitter or Instagram, because I'd love to see it. And make sure you look out for my video next week, which is all about the LOFAR data that's been released and all the science that they've done with it. But until then, everyone, happy stargazing. So this bright ring of emission around the outside is what's known as a photoplanetary. Proto. It's like Frodo. Mr. Proto. Why my brain goes to such strange places? Now we can see with is it PDS 70 or PD 570? Fuck. Ooh. Handwriting, Becky. Write neater. Hello. Unlock. Oh. Benisti, not Beniski. God, handwriting, Becky! PDS 70, for shit's sake. The whole process is autonomous. I kind of want to say like Thomas at the end. Like Auto-Thomas. Auto-Thomas will collect a sample. We're one of a kind, no category. Too many years lost in the story. We're free to take our crown and glory. We're exomoons. We're moons.